Greetings and welcome back. So we're thinking about the Turing instability, and I've given several vignettes about it. The first was, in a certain sense, an introduction to Alan Turing and his work, and the second one was an attempt to investigate the instability of the two-cell system. Now what we're going to do is we're going to broach what Turing himself referred to as the artificial ring of cells. And what that really means to us is that we're going to have periodic boundary conditions. So, if I have these hexagonal cells, the way I want you to think about it is that they make a ring. And what that means is that if I go all the way around the ring, then I've got to come back to where I started. And that signifies a certain kind of periodicity to the solutions. So this is like the two-state model of transcription, a somewhat technical discussion, and some of the technicalities have to do with things that one gets a feel for with practice. And what I'm talking about, for example, is that I'm going to use complex exponentials, and that's just to remind you that I can kind of freely go back and forth between these two worlds, meaning that I can either choose to talk about sines and cosines in the languages of e to the ix and e to the minus ix, or I can choose to work in the world of cosine x and sine x. And, my counsel to you, assuming that you want such a thing, it sounds very pretentious, but, when I first started learning about this, I found it really troubling. And the first time I heard about these kinds of things was in the context of the damped harmonic oscillator. So, you have an oscillator that's subject to some sort of forcing, and all the trouble, if you like, is this term, which is the damping term. And what I was going to say is that it's just much more convenient, at least to me now in retrospect, to work in terms of solutions of the form e to the I omega t, as opposed to using cosine omega t in these kinds of problems. And similarly, in what we're going to undertake here, we're going to be using complex exponentials because it's really more transparent. The math is by far easier. But if you're not used to thinking about this particular formula, then it may seem obscure. And all I can do is say that, this might be one of those vignettes where we're a little bit shading towards the knowing about as opposed to the knowing. If you want to be in the knowing category, it means that you're going to have to fill in some of the details that I'm going to sort of, with lightning speed, pass right on by on the assumption that we're good to go on, for example, e to the ix is cosine x plus I sine x, and I'm going to assume that we're good to go on e to the x is approximately equal to 1 plus x squared over 2. So we're going to use that kind of stuff with fluency, but with the charge to you that, the way to learn these things is to go do them yourselves. Okay, so we're going to consider this system, and we have a collection of cells. And what I want to do is I want to start by writing the dynamical equations for the rth cell. And the way that I'm going to do this is I'm going to first write down the chemistry term like we did last time, and then I'm going to write down a diffusive term. So we'll look at these in turn. So this first piece, as I say, is chemistry. And what we've done is we've generalized what we saw before, where I previously had f of x and y was equal to, I should say Turing did, 5x minus 6y plus 1. That's what we had previously. And we're now going to use something more sophisticated, something non-linear, and in fact we're not even going to specify any particulars about the nature of f of x, y. So this is the chemistry term. It tells us how x and y conspire to lead to either an increase or a decrease in xr in that box. And then on the right-hand side, we have a diffusion term. And the way to see that is, why don't we set xr equal to 0, And what we'll see is that if xr is 0, these two terms are going to contribute with plus sign to increasing dxr by dt. That's because stuff is flowing in from the two adjacent skyscrapers in the histogram, if you'll go back to that language that I've used in the past. On the other hand, let's assume that these two are 0, and then what we will see is that there's a minus sign, and what that corresponds to is jumping out of the xr box and into the xr plus 1 and the xr minus 1 boxes. So this thing is basically saying that there's a flux to the right and a flux to the left, or another way of saying it is that the three adjacent guys, xr and then r minus 1, and r plus 1, that they're keeping track of each other's balance of particles, and all the molecules are flipping coins, and they're moving left or right according to heads or tails, and that leads to the rearrangement that you're used to from earlier in the term. Okay, and then we have a second equation, which is dyr by dt, and I'll write that as g of xr and yr plus dy now, and then yr plus 1 plus yr minus 1 minus 2yr. And once again, this is the diffusive term, and this is the chemistry term. It's different. In other words, the y chemistry is different than the x chemistry. And again, I'm leaving it unspecified. And this is the diffusion term. Now, there are, how many equations are there? There's 2 times n, where n is the number of cells in the ring. So I guess I would say it this way: there's a total of 2n ODEs, where n is the number of cells in the ring. But we're going to find, and this is one of the cool things about this, we're going to find that we only have to focus on the rth box. Because of periodicity, this is something that in solid-state physics is known as Bloch's theorem. Because of periodicity, we know that when we go one full traverse around the ring, we have to come back where we started. At any rate, that gives us a character for the solutions, and you'll see what I mean by that. So now I'm going to say that the fixed point is equal to h comma k. That implies that f of h comma k is 0, and that g of h comma k is 0. That's what that implies. That's what I mean by fixed point. So there's some fixed point of these f and g functions. I'm not worrying about what it is. I'm just saying that it exists. And now what we want to do is we want to find xr of t, which is h plus little xr of t, and big yr of t is k plus little yr of t. So this is our perturbative analysis. In the sense that what we're considering is a small perturbation around the fixed points h and k, and we're asking, is the system going to be unstable? So the concept is substitute these into the ODEs, and what will come out of that is we'll be left with dxr by dt. If you go back to the notes from the previous case, this is an example of where I'm kind of rushing along. F of h plus xr of t, y plus, k plus yr of t, and then plus dx, xr plus 1, plus xr minus 1, minus 2xr. This is lowercase x, and I've been lazy by not putting the time dependence in these terms. Now, why did this turn out this way? It turned out this way because, for example, if you look at this guy, what you would have had was h plus xr plus 1, h plus xr minus 1, minus 2h minus 2xr. So the h's all cancel out. So that's the reason that those guys are gone. Now I'm going to note that f of h plus xr of t and k plus yr of t can be rewritten as approximately equal to f of h and k, and then plus df by dx evaluated at h and k times xr plus df by dy evaluated at h and k times yr. So this is the linearization. We call this linear stability analysis, and in this case the linearization means that we pick off only the pieces that are linear in our field in our variables xr and x and yr. So the consequence of this is that we may now write dxr by dt, and now I'm going to be a little bit more, what do I want to say, a little bit more notationally sophisticated. So this thing is going to be of this form. Where I've now defined this coefficient as df by dx evaluated at the fixed point, and a12 is df by dy also evaluated at the fixed point. So that's what we get for the y or the x equation. Now we need to let's see. Sorry, I need to add a few pages. So I'm just going to straight away write down the yr equation, and that's going to be equal to a21 xr plus a22 yr, and then plus dy, and then yr plus 1 plus yr minus 1 minus 2yr. So that's my equation for yr, where now a21 is equal to dg by dx evaluated at hk, and a22 is equal to dg by dy evaluated at h comma k. So that's the situation. And if you were to shift over by 1 by symmetry, you know, you'd get basically the same equation, but you would have dxr plus 1, and then, you know, this part having to do with the diffusive terms would involve an xr plus 2, an xr plus 1, and an xr, etc. But there's because of the symmetry, the trial solution that we're going to bring to the table is of this form. So the trial solution is xr of t is equal to, I'm going to call it x0 of t e to the I 2 pi ra divided by the wavelength of my perturbation, and yr of t is equal to y0 of t e to the I 2 pi ra over lambda. So this is what is the nature of our trial solution? The nature of our trial solution is that we have a periodic wave of wavelength lambda, and A is the cell size, or, you know, the size of the lattice on our ring. Okay, so that's the trial solution, and now what I'm going to argue is that we can take this trial solution, these things, and we can plug them in to the differential equations that we obtain. So that's the plan. We want to plug those things in. So let me do that. It's going to maybe be a little bit hard, but so I have e to the I. Okay, I need to write bigger. E to the I 2 pi ra over lambda, and then dx0 by dt is equal to, then we had a11 x0 e to the I 2 pi ra over lambda plus a12 y0 e to the I 2 pi r a over lambda, and then plus dx x0, I'll put that out there, and then I have e to the I 2 pi r plus 1 a over lambda plus e to the I 2 pi r minus 1 a over lambda, and then minus 2 e to the I 2 pi r a over lambda. And all of this right-hand side needs to be multiplied by x0. Sorry. Got a little carried away. I already did that. X0 is already there. Sorry. Forgive me. This is all fine. Okay, and then we have a similar situation for y, e to the I 2 pi r a over lambda, dy0 by dt. That's going to be a 2 1 e to the I 2 pi r a over lambda x0 plus a 2 2 y0 e to the I 2 pi r a over lambda. You know, I'm sitting here just doing this algebra, but I encourage you while you're sitting there to, maybe not even listen to me and instead just write out for yourself all the terms that come from doing what I said, which is doing the substitution. That's the aspect that we're up to. We're trying to do the substitution. So now multiply both equations by e to the minus I 2 pi r a over lambda. And what we'll be left with is dx0 by dt is equal to a11 x0 plus a12 y0, and then plus dx. And then we will have e to the I 2 pi a over lambda plus e to the minus I 2 pi a over lambda, and then minus 2. And we will have dy0 by dt is equal to a21 x0 plus a22 y0 plus dy, and then same thing. Just copy it. Okay, so far so good. So what we've done is we have now turned this into a differential equation, two differential equations, for the time dependence of the amplitudes of these cosine waves, or in other words, of these waves of x and y variation. And final point is, let's Taylor expand. E to the ix is approximately equal to 1 plus ix minus x squared over 2, and e to the minus ix is approximately equal to 1 minus ix minus x squared over 2. If I plug that in upstairs, let me show you what you should expect. So if you plug that in, well, let's just look at this. So I plug both of these in right here. So I get 1 plus 1, which is 2, and that subtracts off this 2 over here. So those constants are gone. I have plus ix and minus x, so those guys are also gone. So all that survives is 2 copies of x squared, where x is 2 pi a over lambda. So when all the dust settles, we're now ready to write dx0 by dt is equal to a11 x0 plus a12 y0 plus, no, it's actually going to be minus dx, and then 2 pi a over lambda squared times x0. And similarly, dy0 by dt is equal to a21 x0 plus a22 y0 minus dy, 2 pi over a squared, lambda squared, times y0. So finally, whew, after all the dust settles, we're back to one of these eigenvalue problems, and we have a11 minus dx 2 pi a over lambda squared, a12, a21, and then a22 minus dy 2 pi a over lambda squared, and that's times x0, y0. Okay, what I'm arguing, what I want to point out is that this is now in the same form as the one cell case that we did for Turing. In other words, the scheme was we needed to solve two coupled linear ODEs, and we posited solutions. So the trial solution now would be x0 of t is equal to x bar or something, e to the sigma t, and y0 t is equal to y bar, e to the sigma t. We try that, and that leads to finding the eigenvalues of this matrix and asking the question whether the largest eigenvalue is greater or less than 0. If sigma is greater than 0, the perturbation grows in time. Clearly, sigma will depend on lambda. In other words, for every choice of lambda that we make, we'll get a different eigenvalue problem. We'll have a different quadratic equation to solve. And so, depending on the choice of lambda, we'll get different coefficients, and therefore we'll get different eigenvalues. And we're asking, what's the largest eigenvalue? What wavelength gives us the largest eigenvalue? And that's what's shown over here. So what I'm plotting for you is the wavelength of the perturbation, and then I'm plotting the largest eigenvalue. And what I want you to appreciate is that the maximum is here, which means there's a finite wavelength instability, and this will be the fastest growing mode. In other words, if I got some undulation in the x and y fields, the wavelength that would dominate in the long time limit would be the one that is here. It's kind of the kind of thinking that we have in mind. So where are we? As I said before, this is a little bit in the spirit of knowing about as opposed to knowing. I hope that you just have a sense of how we would go about handling the more nonlinear version of the Turing instability. The things that I have up my sleeve to finish all this topic up is I'm looking forward to now doing the continuous version. So these are discrete cells. And what I'm going to do next is I'm going to do the continuum reaction diffusion. It'll be like what we had for Bicoid. So we will have a partial differential equation, which will tell us how both the time and the space dependence of x and y. So this x and y will be continuous fields, and we will ask exactly the same question, which is there a finite wavelength instability? And we'll find the same answer, which is that there is. And this is one of the great themes in sort of mathematical physics, which is passing back and forth between discrete and continuous representations of things. They each have their place. Sometimes it's easiest when conceptualizing something to discretize, and in the end take the limit and send it to the continuum, because often solving partial differential equations is easier than solving, it depends, but that could be easier than solving the discrete cases. Then what I want to do is I want to give you some generalizations, so that'll be a separate vignette, some generalizations of Turing to other architectures, rather than just we have the activator and the inhibitor. We'll think about triangles, where we have 3 molecules of interest, and we will also think about the work from Erwin Frey that I told you about, in which he considers the chemistry to be conservative. That would correspond to, in this case, if we added plus fxy here, we would subtract fxy down here. That is what we would mean by conservative chemistry. What you produce, you're basically making sure that the total number of x's and y's stays the same. So I'll comment on that. I probably didn't say that quite right, so I'll have to rethink that. But so that's what we have on tap, and then once we finish those things, then we're going to turn to what I will call the theme of life as defiance.